In number 11, I'm going to solve the following inequality in interval notation. It's what's called the polynomial inequality. So for a brief moment, I'm going to take the factored form and set each of the factors equal to 0. Sorry, I don't need the parentheses there. All right, so that tells me that it's -2 and +5. Okay, so what I want to do is I want to make a number line, and I want to label those two numbers. So those two numbers are actually part of my solution. What I don't know right now is whether it's between the two numbers, if it's away from the two numbers, if the two numbers don't even matter. I mean, this is where I have to sort of sign test it. So I'm going to pick something less than -2, like -3, something between -2 and 5, like 0, something bigger than 5, like 6, and evaluate the factored form. And again, the nice thing about factored form is I can very quickly decide if something is positive or negative. So let me write that in there real quick. 0 plus 2 squared, 0 minus 5, and 6 plus 2 squared, and 6 minus 5. Okay. Now, the nice part about those squared things, anytime I square a positive or a negative, I always get a positive result. So in all three cases, that first piece will be positive. The interesting piece is what's happening in the second half. So -3 minus 5 is negative, 0 minus 5 is negative, and 6 minus 5 is positive. Okay, so what happens when I multiply a positive or negative? I get a negative. All right, so in my chart, I now know where the positive and negatives live. I wanted, according to my inequality symbol, I wanted less than 0. So that's going to be where 5 is. Okay. Now, can I include my numbers? So what happens at -2 and at 5? It actually equals 0 at those two places. So I don't want to include 5. I want to put parentheses around those things. But anything in between is fine. So my solution is -infinity up till -2 union -2 to 5. There you go. Number 12, we're asked to use rational zeros theorem. Find all the real zeros of the polynomial. Okay. So this is that PQ process that we looked at earlier in the course. So I want to start with the last number, which is 8, and the first number, the leading coefficient, which is 1. And I want to make a list of all the possible factors of 8. So 1 and 8, 2 and 4, and that is it. And then 1 happens to be just the number 1. So my possible rational zeros are going to be plus or minus, and then I want to take every number in the first list divided by every number in the second list. So 1 over 1, 8 over 1, 2 over 1, 4 over 1. So I end up getting actually 8 possibilities, plus or minus 1, plus or minus 8, plus or minus 2, and plus or minus 4. Okay. Now, it is a cubic, so this is where I set up synthetic division. And let's see, let me set that up real quick. So 1, -3, -6, and 8. All right, and this is where I guess. I have 8 numbers. I'm just going to take a random guess, and now I'm lazy, and I'm going to start with 1. And I'm going to see if 1 will work. So drop the 1 down, multiply. That gives me -2, so -2 there. Oh my, did I get it right the first time? Wow, good for me. All right, so 1 works. Okay, so we have to sort of think about, let's put my 0 here. So one of my zeros happens to be 1. And this brick of numbers right there, that actually translates to x squared minus 2x minus 8. And so from here, I don't want to look at rational roots. I want to go on to something else because we know lots of stuff about quadratics, and honestly, factoring is going to be a lot faster than anything else we can come up with. So let's see, that would be x and x, 4 and 2. I want the 4 to be the negative and the 2 to be the positive, which, if I set that equal to 0 and solve, translates into -2 and +4. Now, I don't see a blank for this, but on the test there's a blank for writing factored form. So the factored form is just collecting up all of those terms. Now we can see x plus 2 and x minus 4, and then we just have to remember the 1, that it crosses at 1 really means in factored form x minus 1. Again, sort of does that sign change on us. Number 13, we got a couple of questions that are actually connected here. We're asked to find the inverse, and then we're actually asked to find the domain and range of the original and the inverse. So let's start with just finding the inverse. So in this case, we have we're going to replace f of x with y, and then I'm going to interchange. So it's my way of saying I'm going to do something different with x with y. So x equals 3 over y plus, 8 plus y. All right, now my goal is to solve for y. So I'm going to multiply across, so x 8 plus y equals 3, and I'm trying to isolate y. So in this particular example, I don't see a reason to distribute, so I'm just going to divide the x out. Can I come up here? Then I can subtract off the 8, so y equals 3 over x plus, minus 8. And that would be our inverse. And so that's a perfectly good form to have our number in. If I want to do a common denominator, so if I want to bring it into one single fraction, that's fine. That would be 3 over x minus 8 times, and then I just make it have a common denominator. So 3 minus 8x over x would also be another form for our inverse. So either the first one or the last one, those are perfectly good inverse forms. Okay, domain of f of x. Okay, so on that one, I want to just look at the original function, and the only number I can kick out is -8. So negative infinity up till -8 union -8. I'm having a hard time writing 8. -8 to infinity. For the inverse domain, looking at the only number that we want to kick out of the denominator is 0. So negative infinity up till 0 union 0 out to infinity. Okay. Now, interestingly enough, our domain and range are inverses of each other, right? So that means they just switch places. So I can switch, let's see if I can come over here. So my range then for my original function is going to be the domain of my inverse. And then my range of my inverse is going to be the domain of the original. Number 14, we're asked to graph an exponential. We talked about doing a mapping approach to this. So we're going to sort of think about the parent graph. So in this case, our parent graph, parent function would be 4 to the x. And we talked about that there's 3 points that we can always identify and the asymptote from the parent. So in this case, we would want -1, 1/4, 0, 1, and 1, 4. And so then I'm going to look at my mapping rules. So in my mapping rules, I'm looking inside the function, so inside the exponent component, inside the exponent. So it says x minus 2, so that means I'm opposite of what I see, so x plus 2. And y is going to be based on the outside, so y plus 1. So that's what I need to do, is I just need to add 2 to the x's and add 1 to the y's. So let's see, let's add 2 real quick. -1 plus 2 is 1. 0 plus 2 is 2. 1 plus 2 is 3. And then 1/4 plus 1 is 1 1/4. 1 plus 1 is 2. 4 plus 1 is 5. And then we'll plot those points. So 1 and 1 1/4 is right there. 2, 2, and 3, 5 right there. Okay, and so that's a real quick sketch of that picture. Graph 5 plus log base 2 of x minus 4. Okay, same idea as last time. I'm going to quickly identify the parent graph, which in this case is log base 2. Sort of works with the reverse of the exponential. So my ordered pairs for the parent would be 1/2, -1, 0, 1, and 2, 1. And then I want to look at the mapping here. So again, x is based on the inside, so it says -4, so I'm going to add 4. And the y is on the outside, so that'd be y plus 5. So I'm going to do that to all of my points. 1/2 plus 4 is 4.5. 0 plus 4 is 4. 4 plus 2 is 6. Let's see, hold on. Make sure I got that right. Okay, sorry, I just realized I goofed. This is switched. So it should be 1, 0 for the parent. Okay, because that was looking weird. That should be small to big, and it wasn't working that way for me. So that actually puts that at 5. Okay, y values. Let's make sure I don't make this a mess up on this. -1 plus 5 is 4. 0 plus 5 is 5. 1 plus 5 is 6. Okay. So 4.5, 4, right there. 5, 5, right there. And 6, 6, right there. And again, I have to understand enough about the graph to recognize that it's a logarithmic. So there we go. Okay, I want to solve the following log equations. First task is with given 2 log statements, I want to try to get the logs together. So I see that there's a 2 out front, so I have a log property that'll let me bring that up as an exponent. So x minus 8 squared times, because if we're adding log, actually, ooh, that's actually not true, because this is log base 4 of 4. That's actually one of our properties. That is equal to the number 1. All right, well, this got a lot easier for us. Okay, so from here, so log base 4 of x minus 8 squared. I'm going to bring the 1 over, so 2 minus 1 is 1. Then I'm going to convert it to exponent form. So 4 to the first equals x minus 8 squared. And at this point, it's about using our quadratic skills then. So I notice that since it's squared, I'm just going to take the square root. So plus or minus 4 on that. X minus 8. Let me go back up a second. Okay. And then I'm going to add 8 to both sides. So I get 8 plus or minus the square root of 4 equals x. Now that's 8 plus or minus 2. And I can split that up into two answers. So 8 plus 2 and 8 minus 2. So I get 10 and 6. So before I get excited about that, I want to come back up to the original and just make sure if I plug a 10 or a 6 in, I don't violate a domain restriction. So if I plug in 10 minus 8, 10 minus 8 is a positive number, so we're good. 6 minus 8, however, it gives me negative 2, and I can't take the log of a negative. So 6 actually violates the restrictions. So he does not make it, but 10 does. So the correct answer for that one is 10. And then the other equation, 3 to the 2x minus 3 equals 1 over 27. What I want to do here is I want to convert the 27 and 3 to a common base. So 27 is actually 3 cubed. And the fact that it's in a fraction means we're going to bring up negative exponents. So 2x minus 3 equals 3 to the negative 3. So now that the bases match, I'm going to set the exponents equal to each other. So that's 2x equals 0. That means in this case x is 0. And that's a perfectly fine answer. Okay, number 17 is an exponential growth problem, and more specifically it's a double life. So our double life formula is p equals p naught times 2 to the t over double time. And let's see, if the population doubled in size over 24 months, so our doubling time is 24, and the current population is 60,000. When will it be 300,000? Okay, so I'm going to go ahead and say 300,000 equals 60,000 times 2 to the t over 24. Okay, so right now my variable is buried inside the exponent there. So what I want to do is I want to isolate out that expression by dividing. So I'm going to divide both sides by 60,000. Let's see, the zeros are gone, so it's really 30 over 6, which is 5 actually. So 5 equals 2 to the t over 24. Then I want to take the ln of both sides. And what that allows me to do is that allows me to bring the exponent out front. So t over 24 times the ln of 2. Then I want to take 24 times the ln of 5. And I want to divide that by the ln of 2. And that equals our time. So that I'm going to go to a calculator and just type that in. So 24 ln of 5 divided by ln of 2. So I get 55.72. All right, so 73 actually rounds up to 3. So 55.73 months. All right, number 18. For the following matrices in reduced row echelon form, give the solution to the corresponding equations. Okay, so the trick here is to recognize what form it is and then answer the question that corresponds to it. So in the first one, I'm going to look at the bottom row and I see 0, 0, 1, 1. Okay, what that tells me is that z is 1, and so I can use back substitution to figure out x and y. So then I'm going to go to the second row, which is 2y plus z equals 3. So fill in what I know. So 2y plus 1 equals 3. That means 2y equals 2, and so y is 1. All right, noticing a pattern here. Then, kind of star that. Then I want to look at the top equation. The top equation says x plus 2y plus 3z equals 6. And I already know y and z, so x plus 2 times 1 plus 3 times 1 equals 6. So, oh goodness, what would x be? Well, let's see, x plus 5 equals 6, so x is 6. Yay! So our ordered pair then is 1, 1, 1. Okay, so that's the first type. Second type, again, look at the bottom row. Bottom row is 0, 0, 0, 1. Okay, so what that says is 0x plus 0y plus 0z equals 1. How often will that be true? That's actually never going to be true. So that's an example of no solution. And then the last case is, again, bottom row is zeros. So 0x plus 0y plus 0z equals 0. That actually is always true, so there's an infinite number of solutions to this. But many solutions actually will not get you credit. You need to tell me of what form. So this is where I took, let's see, 2y plus z equals 3. So I'm going to rewrite this equation in terms of y. So 2y equals 3 minus z, and then divide everybody by 2. So I get y equals 3/2 minus z over 2. And I'm just going to put a little reminder next to that so I don't forget it. That's a z, by the way. Then the top piece says x plus 2y plus 3z equals 6. And I'm going to substitute in that expression that I just found for y. So 3/2 minus z over 2 plus 3z equals 6. Now the nice part is I had a fraction for a second. I'm now just going to get rid of the fractions. So if I distribute the 2 in, the fact that I'm dividing by 2 in both cases is going to essentially cancel out the 2. So I end up with 3 minus z and then plus the 3z equals 6. So I can combine the z's to get 2z there. And then I'll bring everything over except for the x. So x equals negative 2z. Take the 3 over, so that's 6 minus 3, so that's actually plus 3. And now I've got a formula in terms of x. Okay. So my solution is going to be the ordered triple where x is negative 2z plus 3, y is 3/2 minus z over 2, and z is any number. And so now what I've said is, yes, there's an infinite number of solutions that'll make this true, but honestly, it's z that matters. So you tell me z, and then I can define the other variables in terms of it.